Hey, how is everyone doing today? I'm your host, Joe Fernandez, a part of the marketing team over here at Tech 30. Thank you all so much for tuning into our webinar today. We are fortunate enough to have Trevor Silence, our applications engineer from Tech 30, as he will be presenting this webinar's topic of Mathcad Prime functions and automation. We also have Ron Zabilski, a solutions consultant for Tech 30. And just as a reminder that if anyone has questions, please drop them in the chat box or the question box, and we will answer them at the end of the webinar. And now I'm going to be passing it over to Ron, and he will give you a little background information of who Tech 30 is and what we offer.
Thank you, Joe. To everybody, welcome to the webinar. As we conduct this, we highly encourage you to engage with us. You'll be able to ask questions and leave comments on the sidebar of the GoToMeeting panel. Even if you have questions or comments that don't relate to today's subject, please feel free to ask them, and we can address them either in a follow-up email or in future webinars. As we review this webinar, please view us as a conduit to feedback to the PTC Mathcad product managers and development team. As most of you are aware, Mathcad is more of a niche product within PTC's portfolio. So let's build a community, get the features most requested, prioritized for future Mathcad releases, and again, use this platform as an opportunity to influence the direction of the product development roadmap. We'll also be happy to receive comments or questions by email anytime after this webinar. Thanks. Next. As Joe advised, I'm Ron Zabilski, a solutions consultant with Tech 30. First, Tech 30 is a value-added reseller of PTC products. Second, we're also an engineering services company that helps engineering companies do engineering. We do this with tools from PTC and other OEMs to help our customers make the most of those tools through training and engineering services. We strive to get to know you and your business, and we are at our best when we can actually expand the business of our customers and build a community by connecting them to those who benefit from networking with each other. Next. The company was established back in 2002. We currently have over 80 employees with more than 50 engineers working with us. Our headquarters is located in Mission Viejo, California, but we are distributed around the U.S., meeting the needs of our customers. As a matter of fact, I'm located in the Boston, Massachusetts area. Tech 30 has small business status in 4 business units. The first is PTC software. We also do 3D printing and additive manufacturing. As mentioned earlier, engineering services, and we also have an arm that does Siemens software. We can provide a wide range of engineering services, including mechanical and electrical design, static, dynamic, and kinematic analysis, design for manufacturing, assembly, and additive manufacturing, new PLM implementations, system integrations and migrations, as well as training for all the above services. Tech 30 can provide services to areas of engineering and design where you currently do not have the expertise, or supplement your existing in-house capabilities. Next. As a value-added reseller for PTC, we focus in these areas, these software products: Mathcad, Creo, Windchill, ThingWorx, and Vuforia. Next. We also offer a broad portfolio of 3D printers from companies that we represent. You can take a look at these technologies on this page. I won't go into a lot of detail here, but just keep in mind that we focus on industrial use cases for 3D printing, both in plastics and metals. We help our customers make additive manufacturing become part of their finished product, or use it for tooling, fixtures, and jigs. If you have any interest in these areas, please contact me afterwards and we can have a conversation about your use cases. Next. We don't have the correct slide on the screen. Oh, there we go. So today's webinar is about Mathcad, and the main reason why you're all here today. Before I pass the presentation over to Trevor, I want to inform you of the services that Tech30 does provide around Mathcad. We not only sell the software, but we also provide unique value-added services to ensure that our customers make the most of their software purchase. But first, what is the value of Mathcad as a software? They are automation or reuse of calculations, collaboration, sharing those calculations and worksheets in an easily understood document, and the natural math, that is creating calculations that you would use on paper so everybody can understand them with no coding or development experience necessary. One of the unique services that Tech30 offers is our conversion services for Mathcad. Customers often see the value of standardizing on such a tool as Mathcad to make it more collaborative and efficient within their organizations. This will become more evident, especially after you see Trevor's presentation. However, one of the barriers to adopting Mathcad is getting your calculations from other formats into Mathcad. We're all busy at our primary job functions, so who has the time to bring legacy Excel files, hand calculations, MATLAB files, or even Mathcad 15 files into Mathcad Prime? That's where Tech30 can come in. You give us your calculations in whatever format they're in, and we'll convert the data for you and hand you your new Mathcad files. We'll even train your users to use Mathcad to ensure maximum use of the tool. So if this situation describes the state of your engineering calculations, please let us help you. Next. With that, I'm turning the webinar over to Trevor to show you different ways of customizations within the Mathcad. So it's all yours, Trevor.
Thanks, Ron. All right, so let's get right into it today. Here's a little overview of what we're going to be talking about. So we're going to talk about defining some custom functions, both in one variable and in more than one variable. Also show you a little bit of how to build in those custom functions. It's a pretty involved process, so I won't go too in depth with that, but if you are interested, please let us know and we can do another follow-up webinar specifically on building in your own custom functions. After that, we'll talk about defining custom programs. We'll go through conditional programs using if statements, recursive programs that call themselves as they iterate. We'll go into for loops, while loops, and some intermediate complexity programs. You can see some examples of custom functions and custom programs on the right-hand side of the screen. We'll get into these a little bit more as we go on. So some use cases for this technology within Mathcad Prime is you can save a lot of time with repetitive calculations by using custom functions. You can test values easily without having to rewrite the whole thing. And then custom programs are great because you can produce vectors that fall within a certain condition. You can perform the same calculation over and over again using a previous result, which we'll do a little bit when making a factorial and using recursion. You can also get a loop going through a range or until a certain value is obtained or a certain criteria is broken. And custom programs are great because you can kind of group a lot of calculations in one box and it'll just spit out the answer you want instead of having to go through all these intermediate steps. So to get started, we'll just talk about the custom functions. So the basic way to define a function is to type some kind of function name. In this case, it's f, and then we can specify what input variables we have. And then when we define the function, we'll have to use those input variables as well. And then, so like, for example, we have one in one variable, which is just a line equation there where mx plus b is equal to f of x. So you can see we're using our x as our input variable, and it's also referenced in the equation. We can do something in two variables where we get the volume of a cylinder. And then we can also do a volume of a square or cube or something like that. So I'm going to hop into Mathcad now, and we'll get into how to make these custom functions. So to start, I'm just going to type right here on the screen. I'm just going to use f as our function name, and then I'm going to put x as our input variable. And then I'm going to define just a basic polynomial equation, x squared plus 2x minus 1. So once I have this defined, you can see I already have these values, this input value of 1 plugged in here, and so that gives us a result of 2. You're also able to pass a vector into this function. So I have a vector of x here where it's 1, 2, 3, 4, and we can see our results at the end of when we plug f of big X here, we get a result of 2, 7, 14, and 23 that corresponds to each input number provided here. So pretty straightforward. Similarly to how you'd write it out on paper, you can pretty much get the result just from typing it out the same way in Mathcad. In this example, we're going to do more than one variable, so 2 variables. And this is going to be this equation for radius of a circle. So I'm going to define this and have a square root here. And for that square root, you can always add it in operators. But I also use the / as you see in the tooltip there. And so that's a shortcut to get that square root. And so I'll just do x squared plus y squared. And this should give us the radius of a circle. When we plug in the two points here, 1 and 2, we get our radius of 2.236. Likewise, I can plug in another vector here. So I'm using the same vector as above, the 1, 2, 3, 4. And I'm also using this b vector. So I've defined it in a row just to save some space, but I put a transform here so that it'll put it into a vertical vector when we plug it into our g function. Another one we'd like to look at today is a surface area of a box. So we already have defined the input variables of length, width, and height here. So I'm just going to define the actual function. So it's going to be 2 times length times width plus width times height plus length times height. And so this is each one of these is a side of your square or your box. And then we're just going to multiply that by 2 because we have 2 of the same side for each cube. And so when we do have these input values of length of 5, width of 5, and height of 2, we get a surface area out of 90. There are some built-in functions we'll touch on briefly. So we've done webinars on these in the past, but I would like to show you guys that it's possible to use them as a quick demo here. So I'm just going to use that initial polynomial we defined up there, our f function, and it's going to be x of 0. For this root function, we do have to provide a guess value, and in this case, the guess value is 1. So here we have a root of our f of x0, where our guess value is 1, and then we get our root out as 0.414. Polyroots does something similar to root, except it'll provide all the roots to that equation. I've actually mapped the equation out here in just coefficient terms. So this is the term that does not correspond to any variable. This 2 corresponds to x, and this 1 corresponds to x squared. And likewise, I have this t here to flip it into the vertical vector space. And so if I do plug in EQ here as our input variable, then I get out these 2 roots, which is one is a negative 2.414, and the other is 0.414. So these are just a little example of some custom functions that you can make and some built-in functions that are already in Mathcad that are pretty useful. So it's really whatever you want to put into these functions you can do, and they can be as involved as you'd like them to be. So if you do want to make your custom functions build in, it does take a little bit more work. It is a little bit more involved, but it is possible. So it requires writing some source code in C or C++, or if you have Fortran code, you can wrap that in C wrapper. And then you'll need to compile the source code using a compiler like Visual C++. And from there, you're going to link the object files using a mcaduser.lib library that's provided with your Mathcad installation. And this will create a DLL. And then you just have to place that DLL in the custom functions folder. And if you would like to see an example of this, or if you want a whole webinar dedicated to just building in these custom functions, please let us know. We'd be happy to put something on like this for you. All right, let's get into custom programs. So these are pretty useful. They can't do everything that like a programming language be able to do, but we can do quite a lot. So most programs will start with something called a program structure, which is these 2 double bars here. That's what they call a program structure. And within that program structure, you can use if, else, elseif statements for conditional programs. You also have the option to use while and for loops. Some of these keywords and modifiers, you don't actually need to have a program structure there. You can kind of just type it into the worksheet without the initial program structure. So I'll show you guys how to do that a little bit as well. The left arrow will be used to assign a variable value within the program structure. So on this right-hand side, we have I is assigned to 0. And this will only apply inside the program structure. So if you have an I outside, it will not be overwritten by that 0. You can also use something called a try and not error, and this will test expressions that may be continuous or that may result in errors. For example, if you have to divide, if one of your variables will end up resulting in a division by 0, you might want to use a try and on error to catch that so that you can actually get a result out. It's also possible to use symbolic evaluation to create a program, which I'll show you a little bit later as well. To change the way that a program is flowing, there's three keywords we can use. A return will halt the program and return the current result. A break just breaks the current loop, and it'll return the last value calculated. And continue will just skip the loop and go on to the next one. So on the right-hand side, you can see we have 2 returns here. One is a return of I. So if the product is equal to the term, we'll return the I value here, which is a factor. And then if it's not, if we go through this loop and there's no product that is equivalent to the term, then we'll just get a return of 0 here. So you can see how you can use these different breaks and flow editing commands to change the way that your program behaves depending on the conditions that are present. So I'm going to hop into Mathcad again, and we'll get right into doing some automation here. So the first one is just a simple program. I'm not even going to use a program structure for this. So I just typed 4, and I hit Control J there to populate the inputs and things needed for this program. You can also go to this programming button and click on 4 here, and it will do the same thing. But Control J is a good shortcut if you just want to type it out and not have to do too many clicks. So I'm going to use I as our variable, and then I'm just going to go for I between the range of 1 and 7. So it's going to iterate through 1, 2, 3, 4, 5, 6, 7. And then I'm just going to have a simple program where S is assigned as S plus I. And so if we do this and we hit this equal sign, then you'll see that we produce a value of 28. So this is just adding up each value in this 1 through 7, and we get our answer out as 28. You can also include a program into the equation. So here you see we have this integral, this definite integral, and we also have some addition going on, and I can just put in an S here, similarly to what we did before. So S is assigned as 0. And I'm using space to, I don't know if you guys can see the gray spreading. So as I hit space, it's selecting more and more of that program. And this is how you actually, you can place components in different areas within your program structure. So I'll type 4 here, Control J, I, and then the same thing, 1 through 7. And then I'm going to test if this has a remainder. And then let's see if this remainder, if there's no remainder here when divided by 2, then we'll just continue through the loop. And I have to make sure I hit Control J on that one. And I'm going to hit space and then go to the next line here. And then I'm going to assign S plus I. And then I'll do space again until I get to this line. And there we go. So in this case, I'm just testing the remainder. And if there's no remainder, then I'm going to continue through and keep adding these up. And then this integral is going to be added to our result of the program, which in this case is S down here at the end. And then we're going to add a 3% to that too. So this is just an example of how you can include programs into just a basic equation that you have going on, or an expression that you want to have evaluated. This next example, we're going to do a try and error block. You can see I do have a clear F up here, which is because we've defined F above as that a function where we have the polynomial, the simple x squared plus 2x minus 1. So I'm going to clear that from this point on, and I'm just going to assign this this try. I'm going to hit Control J to populate the rest of the program structure needed for this, and then I'm going to do 1 over 2 minus x. So you can see if we do have x equals 2, we're going to get it should be like infinity, right? So let me put in our constant of infinity here. So normally without this, Mathcad would result in an error, but since we're adding on error here and we're putting infinity here, then Mathcad can actually produce a result. So when we plug 1 into this s function that we have defined, we get the answer of 1 out because 1 over 2 minus 1 is just 1. But if we do plug 2 in here, then we know that this should equate to infinity. And the closest that Mathcad can get to infinity is this 1 times 10 to the 307th power. So in this way, you can actually get a result out instead of just getting some kind of not a number or some kind of error from this and not being able to evaluate it at all. I'll look at conditionals now. So this is just going to be a basic thrust kind of conditional. So I'm going to add a program structure in here. I did that by hitting the right square bracket. So if I mouse over this, you can see next to program in parentheses, you have a right square bracket there. So for this one, I'm going to type if. This is what makes it a conditional. And then we're just going to have a range here. And it's going to go from less than or equal to 0, and then, or greater than or equal to 0 and less than 5. So if your time value is between 0 and 5, then we'll have a result of 100. And I'm hitting space to go through here so that I can enter on the right line. If I hit space here, then it would just keep it within that level. But I want to actually go back down to the first level of the program structure. So I hit space a few more times and then hit enter. And then I'll add an else if statement here. And so in this case, we're going to see if that time vector is greater than or equal to 5 and less than 20, we're going to have a different result out, which will be 80. And then if it's none of these, then we're just going to have a result of 0. And so you'll be able to see in our plot the behavior of this conditional statement. So as t increases, we have it 0, negative, and then once it hits the 0 point, we get a 100 value for our thrust. And then after 5 seconds, the thrust goes down to 80. And then after 20 seconds, the thrust is back down to 0. So this is a nice way to do conditional statements within Mathcad. Our next example is recursive program. I like recursion. It can be a little taxing on the system, but for some things, it's pretty useful to have, especially for a factorial. So let me go ahead and build this program out for you. So we already have our program structure there. I'm just going to add an if statement in. And so I'm going to have when n is equal to 1. So if n is equal to 1, then we're going to have the value of 1 produced. And else, we're going to have n times this factorial function that we have defined. So we're calling it self, and we're just going to have it take a step back from the n that we provided. So this is going to be like 6. So we're going to plug in the 6 here, so it'll be 6 times the factorial of 5, and then it'll go through the whole thing again. It'll be 5 times the factorial of 4, and it'll just keep adding, keep multiplying these up. And so you can see we produced the factorial of 6 here, and we get the answer is 720. Mathcad does have a built-in factorial operator of exclamation mark, which is the traditional one in math. So we kind of made something that already exists, but I wanted to show you guys recursion, and this is a really straightforward, simple method of doing recursion. We can also do a for looping program. In this case, I'm going to create a vector of 1s. So I'm going to type 4 out, hit Control J, and then I'm using I again as my internal variable. I'm just going to do 1 to n here. And in this case, I'm going to do R of I, and this is going to be assigned as 1. And so we're going to return, I'm just going to return R at the end of this, and make sure I hit Control J there again. And so now we have this R, and then this little I is the position in the vector that we're assigning it. And so since we have, we plugged in 3 here, so it's going to be I is 1 to 3, and then it's going to iterate through R1 is 1, R2 is 1, R3 is 1, and then we're just returning that R vector as our result. So here we have our ones function that we created, and then it's cycling through this program and producing this vector of ones here on the right-hand side. We'll also work on creating a while loop. So in this case, we're going to do some kind of threshold program. So I'll do J. I'm going to assign it to 1 to start. And then I'm going to put a while loop here. So while Control J. And then we're also making a vector again. So I do have to use that vector notation with a V sub J. And then I'm going to do a less than T here. So if our value for that V sub J is less than T, we're going to just assign J as J plus 1. And so this is going to increase our index. And then we're going to return this vector of J and a V sub J here. So it should tell us the index and the value that corresponds to that index. So when we provide it with this V vector here, we have these terms 1.69, 4.27, 6.33, 3.56, and 8.99. And then we are assigning our threshold to be this T, which is equal to 5. So as you can see, it stops after it hits the 6.33. So that 6.33 is past our threshold of 5. And so this while loop is broken when it hits the 6.33. However, this program is not very robust. You can see we do have this 8.99 here at the bottom, but it isn't returning the index for that. So these are really simple programs, but there are ways to include functionality where it'll select anything that breaks the threshold. A little bit more advanced, but we can get into some more advanced programs if you guys are interested later on. This is like an intermediate complexity program. We're going to kind of experimentally, or not really experimentally, but theoretically find pi. So let me build this for you. We're going to have a bin that's going to collect a set of numbers. And we're also going to use a for statement here. I'm hitting Control J to make that into a program for. And then we're going to do 1 from 1 to n. So, and then let's see. We're going to have the x value, which is just going to be a random number between 0 and 2. And then we have a y that's also a random number between 0 and 2. And then in this, we're going to do an if statement. So if x minus 1 is squared plus y, parentheses, y minus 1 squared. So if this circle equation is less than 1, meaning that it has a radius of less than 1 or 1 or less, we're going to add it to our bin. So we're adding, we're counting how many of these random x and y's fit within a circle of radius 1 located at the point 1, 1 on our Cartesian plane. And so based on how many points we have in our bin, we can return a ratio, which is just the number of points over the number of tries we put into it. And so if I let this populate, I'll walk you guys through what's happening here. So on this side, we do have the exact value of our ratio that we should get. So we have a circle, pi times the radius of 1 here, and then we get our 3.142 for just pi. And then we have our area of a square. And so if we do divide the area of a circle divided by the area of a square, we get the 0.785 ratio here. So if we were to multiply this ratio by the area of a square, we should get the area of a circle out, which would give us pi since we're using a radius of 1 for this example. So on the right-hand side, we're plugging in 700 points. So we're going to use 700 points in our pi finder here. So it's going to go from j as 1 to 700. And then it's going to collect all the points in the 700 tries that actually fit within that circle. And so we're going to do this process 10 times. So we're actually cycling through 700 points 10 different times, since we have defined this j vector as going from 1 to 10, and we have our try vector here with a subscript of j. So it's going to cycle through and do this 10 times, and then that's why we have 10 total tries, and we have 10 ratios that come out of this at the end here. So this is just to give us a more accurate result of our approximation of pi. So we're going to average these 10 tries, which is done in this guess down here. So this is our guess ratio where we have our tries. We're summing them up over all 10 tries, and then we're dividing it by the length of those tries. So that's just 10. And then we get an answer of 0.774. And if we multiply this ratio by the area of a square, we should get something close to pi, which is it's 3.095. It's not exactly pi, but you can see how we did some more complex behaviors here in this pi finder that allow us to produce values and get a guess for what pi would be. So it's just an intermediate kind of complexity program that you can implement within Mathcad. And our last example for programming is to actually produce a program using symbolic evaluation. So we did show this in a previous webinar, but I did want to include it in this one as well, since I think it's a great way to create programs. So in this case, I'm going to do solve for x, but I'm just going to specify fully here. And so when I do that, it actually produces this program out, and you can see we're defining x of y as a function, and we're actually calling it later too. So the result of this symbolic can be called further down in your calculation. And so in this case, since if we weren't going to solve this fully, if I remove this, you can see that it just produces this 3 times y plus 10 over y. But if our y is 0, as in this example, it cannot be computed. So we could do a try and on error type statement as we did previously, or we could just tell this symbolic calculation to solve it fully for us, and then it'll produce this program, and we'll actually get not a number out as a result, because it's saying that when y is equal to 0, it's undefined, and everywhere else the program applies, or the equation applies here. So it's pretty useful to do this. If you don't want to have to write out the whole program or the whole conditional statement, then you could definitely leverage this Symbolics to get this done for you in a little bit of a quicker manner. So I'm going to hop back into our PowerPoint, just go over some takeaways. So basically, custom functions, they can make your life a lot easier. You can test different values in your equation. This will help you save time and reduce the amount of repeated typing and the space needed to test this expression with different values. It's also possible to build these custom functions directly into Mathcad, but that does require some use of coding languages like C or C++ or Fortran, and then compiling that code as a DLL. And programs are especially useful in performing steps of calculations. This allows you to group calculations, and it'll only return the desired result that you want. So definitely great to be able to leverage these tools within Mathcad. And I'm going to open it up to any questions now. Thank you, guys.
Hey, thanks, Trevor. Looks like we have a question from Trevor Stephen Lewis. And his question kind of pertains to what features they're going to have in the future. But his question is, when is the custom function going to be updated to compile against the .NET languages and not C++?
I'm not sure when they intend to update it. I could reach out to PTC and try and get you an answer on that if they are planning on doing that anytime soon. But I do not know currently.
Thank you. We also have a question from David Easler, and his question is, how can alias symbol be defined? Say instead of x, assume to the first power, have x to the first power displayed by default for our documentation convention.
Can you repeat that? Sorry.
So his question one more time was, how can an alias symbol be defined? Say instead of x assumed to the first power, have x to the first power displayed by default for our documentation convention.
I'm not exactly sure if I get the question. Let me see if I could. Maybe I'll have to read that one and reply to that one in an email. I'm sorry.
And we also have a question from Asim Hassan. How do you solve systems of equations in Mathcad?
So for systems of equations, you can use things like solve blocks. You can also do it symbolically. So I believe in one of the past webinars, we did go over solve blocks and symbolic solving a system of equations. You can definitely include a link to that old webinar in our follow-up email after this one. So it is possible. There's a lot of tools that can solve system of equations within Mathcad, and we can include that link for you to inform you on the process.
All right, so David Easer actually clarified. I just pronounced alias wrong. So how can the alias symbol be defined? Say instead of x assumed to the first power, have x to the first power displayed by default for our documentation convention.
Oh, I see. Let's see if I can. I don't think it'll show up here. I'm not exactly. Oh, so I guess if you just type it in like that, it'll show up. I don't know if there's a way to make this happen by default. I've never actually tried to do that, but I can experiment with it a little bit after the webinar, and I'll include a follow-up for that as well in our email. But yeah, I'm not sure if you can do it by default. I don't think that's an option within Mathcad, unfortunately. But I'll double check that, and I'll let you know. Maybe if I do scientific, yeah, no, it's just doesn't matter. So yeah, I'll double check that, and I'll get back to you guys on that one. But I don't, off the top of my head, I don't think it's possible to change that particular default option.
All right, and Asim Hassan, you're asking for a link for the solve blocks and symbolics, which is a previous webinar. Yeah, you can find that on our YouTube channel, but I'll also send you the link to that as well. On our YouTube channel, we have all our previous webinars. And we also have a question from Alex McNabb, and Alex's question is, can you pass units through a custom function or program?
Yeah, you can pass units through both. So let me see. I think I can do it in this example. I'll just need to define maybe it's like seconds here. See if I can select this. So I do have a second unit, and then let me do this here. But we do have to define it as every step. So, but it is possible to do it both in your functions and programs. Oops. Maybe it's not this one. Let me try and just put the newtons here instead of seconds. So I'll just do newtons here. Hopefully. Units. There we go. So we did pass these newtons through. I believe you can do it with seconds as well. I think I was just typing something wrong, but it should still work. And so you do see we have our newton here with our base units shown. I think if I did S here instead of second, then you should get the correct results for the time vector. Let me just try it real quick. The short answer is yes, we can pass them through. Let's see. that doesn't work. So I'll have to experiment with why the seconds aren't working here, but it should usually work.
All right, and then we also have another question from David Easler again. And how do you import external data, XLS files for programming functions?
Sure. So we did a webinar on this as well in the past, but I can show you real briefly. In our input-output tab here, we do have read Excel and Excel component. So an Excel component is actually like an Excel object. So if you double click this, it kind of opens up an Excel worksheet, and you can just type stuff in here. You can include the formatting from Excel right in your document. So if I change like the color here and made this bold, then when I actually close this, you're going to see the same representation here. You can do a read Excel, which you can browse to an Excel file and read a certain number of columns and rows. And then there are ways to do it with just functions as well. I'm not using these buttons, but we can include the webinar on our importing Excel that we did in the past as well in our follow-up email.
All right, thank you. Yeah, and so yeah, we'll be sure to include the link to our YouTube and past webinars as well to all attendees. And Robert Adams, he's requesting a seminar with custom DLL functions. Yeah, we'll definitely consider that for future webinars. Once again, if you would like to request the webinar for Mathcad, at the end, there'll be a survey where you could input whatever topic you would like to see. And we also have another question from James Viss, and his question is there a way to define which Excel cells show up in an Excel component?
Yes, it is possible to do that. Let's see. So you can specify your inputs here, and then you can tell it in the subscript which cells you want to have show up below here. That's a short answer. In our webinar, we do go into depth as far as assigning different subscripts here. I think I can just type in, for example, if I type B1 here, let me see, should be it. Yeah, there is a way, it's in the other webinar for sure. We can follow up with the link to that one. But it does include using these inputs and then adjusting this window here.
All right, thank you. And if you have any other questions, feel free to drop them in the question box. But for now, just to remind everyone again, we also have on our YouTube channel, we have previous Mathcad, Windchill, and Creo webinars as well. So feel free to pass those along to your friends and colleagues. So be sure to subscribe to our channel and follow us on Twitter, LinkedIn to get the latest information regarding our upcoming webinars, get recordings of our webinars. And if you could just stick around for 10 to 15 seconds after the webcast ends, and please leave a comment letting us know what else you would want to see for future Mathcad webinars, and answer our quick survey. That would be awesome. Once again, thank you everyone for attending, and have a great day.